Okay, so thank you everyone for joining our seminar series, USA Asia. So we have two amazing speakers today. So Baskar and Yang. So Baskar is Baskar Ganapathysubramanian. So I'm sorry if I spell your name wrongly. I hope I didn't. Is a chair professor, Joseph and Elizabeth Anderlich Professor in Engineering and Professor of Mechanical Engineering at Iowa State University. And he has a broad interest in computational science, and in particular in computational physics and computational mechanics, among many other things, including stochastic analysis. So Baskar, anytime. Thank you.
Thank you, Gianmarco, for the invitation to present, and happy to present. Good morning, folks in Asia, and good evening, folks in North America. So today I'll be talking about how do you perform direct multiphysics simulations if you're given a geometry, and the geometry is given by a sign distance field, and sign distance field is memorized by a neural network, and that's what we call neural sign distance geometries, right? So an example here is a Stanford bunny, and on the right is essentially a neural sign distance field or a neural level set of this bunny. And if you're just given this neural level set, how do you actually perform simulations on over this geometry, right? Or over a geometry defined by this surface. And this is work broadly where INR means essentially your implicit neural representation, and SBM is the shifted boundary method, which is invented by Guglielmo Scovazzi, who's in attendance today. This is collaboration with a bunch of my very creative colleagues, Adarsh Krishnamurthy, Ming-Cheng Su at Iowa State, Professor Scovazzi at Duke, and Hari Sundar at Tufts. So very quickly, right? So what's the usually when we do complex geometry simulations or complex geometry, geometry representation and conversion becomes the bottleneck, right? So you got to create the mesh, repair the mesh, and there's a lot of manual intervention that's usually required, and then this becomes very, very resource intensive. And then especially when you want to design iterations, this becomes the bottleneck, right? And so several studies have shown, right, about 90% of your effort in commercial analysis platforms, right? So in industry is often used is spent in mesh generation, right? And mesh generation, mesh cleanup, and so on. So there's a big need for automation, right? And automation for design, as well as more recently in terms of if you want to train neural surrogates, right? So as hopefully the next speaker will have some exciting talk on that. Well, especially if you want to create data sets or over complex geometries, then you need some automation. Right? And so there's recently been several exciting advances in AI advances in 3D scene representation. Essentially, what that means is you're able to represent a geometry implicitly, right? Implicitly here is the figure on the bottom left is the earliest work, deep SDF and neural SDFs. And the figure on the right essentially is some exciting work where you essentially train large language models are these large models that can go from verbal prompts, right, essentially to a neural representation of the geometry, right? So this is exciting times we live in, and essentially the question is how do we use this implicit representation of geometry rather than explicit STL file or a point cloud data that we get of the geometry in terms of doing this analysis, right? And so the basic idea here is the implicit neural representation, essentially, a quick definition, right? Implicit neural representation essentially is the zero level set. Think of it as a level set field rather than a surface, a level set field. And the level set field, the zero of the level set field is your actual surface, but you're essentially giving the field everywhere. And you're actually forcing a neural network to memorize this. That is, if you give an XYZ location, right? So the neural SDF or the INR representation gives you essentially some notion of distance to the zero level set, correct? So essentially you represent this geometry with a learned continuous field. So this is the one clear advantage that immediately comes out is you are becoming resolution independent, right? Whatever your mesh size is or mesh, you are essentially learning a continuous field. Second is because it's a sign distance field, the sign of your phi of x, right? So if this is the level set, or the neural level set. It gives you a notion of whether you're inside the geometry or outside the geometry. And then the value of the function, the sign distance field, can essentially allow you to compute how far away you are from the surface of your geometry, right? And is usually exact if phi satisfies what is called the iconal equation. That is, gradient of phi equals 1, then that's exact. And then normals are essentially free to compute, right? So some notion of gradient of phi will give you the outside facing normals. But most current pipelines, right, CAD pipelines, are not don't explicitly use this or directly use this implicit representation, and so they essentially convert this phi of x through either marching cubes or something to a surface representation and then perform analysis. So the question that we asked, that my group and a bunch of collaborators asked is, can we eliminate this intermediate surface or volume meshing when geometry is already given to you implicitly using an implicit level set or implicit neural network, right? And this has tremendous advantages, right? So because the neural networks are small, right? So less than a few MB of data, the memory footprint is very small. And then you're able to represent like very, very complex topologies at arbitrary resolutions if you train this implicit neural representation. And then there's algorithmic alignment, right? So in the previous slide, I showed you a couple of novel techniques that give you from scenes or from point clouds or from STLs. They're able to construct these implicit neural representations using AI-based techniques. So there's algorithmic alignment with things that are already being done. And then there's alignment with computing hardware, right? This works perfectly well on a GPU. So now let's say I'm giving you an implicit level set, right? An implicit neural representation. How do you actually use that in an analysis pipeline? The natural alignment is through immerse boundary methods, right? So immerse boundary methods essentially immerse your surface. In this case, it's an explicitly defined surface, not an implicit surface that I show in this picture, in a background mesh, right? And then you enforce the key questions are, how should the boundary conditions that are originally on this red surface, how are they enforced on the background mesh? And usually via a forcing function. And where is this force enforced, right? So either on the surface or smeared, and there's a whole family of methods starting from 1977, Peskin's method of immerse boundary methods, all the way through various variants, right? So an elegant strategy, right? So that has been very powerfully used in a variety of finite element based approaches, has been in enforcing these Dirichlet boundary conditions using a Dirichlet to Neumann transformation called Nishi's method, right? So I'm very quickly going to walk through what that means, right? So essentially, if you want to enforce Dirichlet conditions here on the red geometry, essentially you convert that by integration by parts and some Lagrange multiplier analysis into 3 additional surface integral terms, right? So first integral is the consistency, second is the adjoint consistency, and the third is the penalty, right? So by adding these 3 terms, which are surface integrals, which are natural to incorporate into finite element analysis, we're essentially converting the problem of enforcing a Dirichlet condition into a Neumann condition, right? Now, but this still requires us to perform a surface integral, right? So that means I need to explicitly know what my mesh is or what my surface is. So this is where the shifted boundary method is super algorithmically aligned with INR, right? So it removes the need to explicitly know or reconstruct actually the true surface, because the basic idea is in shifted boundary method, we shift the imposition of the boundary conditions from the true boundary to a surrogate boundary, right? So if the blue boundary is my true boundary and my background mesh, the closest background mesh surface is this red boundary, the surrogate boundary, essentially I shift my boundary condition from what I'm applying on gamma to this gamma tilde, right? So how are we doing this, right? So it's elegantly simple method. We just shift the imposition of the boundary conditions from the true boundary via Taylor series expansion, right? So if my boundary condition is u equals g on gamma, right, and I'm shifting my boundary to gamma tilde, what should I apply on gamma tilde such that it translates to u equals g on gamma? Simply, I say I am going to impose g tilde on this gamma tilde. I do a Taylor series expansion, and the Taylor series expansion essentially requires my solution dot gradient of my solution dot is the distance to the interface, my distance d, right? Again, remember, this is going to come back. The distance d that requires me to essentially know how far I am from any given point to the surface. And remember that the implicit neural representation gives that to you for free, right? So the INR gives you that information very easily. So now instead of applying my my boundary condition on the true boundary, I'm applying the boundary condition on the surrogate boundary with a simple extension. So wherever I have G tilde, I apply this in terms of this, right? So now the key things are, right? So I need to know D, and D is trivially given by the implicit neural representation. So essentially, you're performing the imposition of the boundary conditions, right, on known surfaces, right, on known boundaries, right, on the known background mesh. And the only thing that you need is D, and D is given to you by your implicit neural representation, right? So an example of this is, say, I'm going to come back to this example often. Just say I'm solving for something on a circle. And this is my true surface. Essentially, when I shift my boundary, I can actually do it on my voxelated or pixelated mesh, and I can essentially get. And we have shown, and Glumo has shown that you can get the expected convergence from FEM, right? So based on the order of your basis function that you use. So now, essentially, what is your core idea here? We replace the question of, oh, well, I'll give you an STL, mesh the geometry, with I'll give you essentially an INR, and all you're saying is I evaluate the implicit neural representation, the neural level sets value phi and gradient phi wherever the solver needs it, right? So once you're given a neural implicit representation, all you do is you infer it. You essentially perform inference and create essentially, in this case, an octree mesh, and then you perform your computational analysis. And what is there in this shifted boundary method? During your element by element assembly on your background mesh, all you do is you query this implicit neural representation for inside-outside classification. And if it's inside, you just throw it away. If it's outside, for flow over an object, right? You calculate your volumetric integral, and then you also need to know the distance to the interface, which is also given by phi, and use that for your surface integrals, right? Then construct your SBM surrogate and corrected boundary terms, and then enable adaptive. We use octrees, and so it enables adaptive octree refinement based on your value of phi. So here are some examples at the bottom, right? So we start with the course on the right is your Stanford Bunny, which is an implicit, defined by an implicit neural representation. We adaptively refine, and we essentially using shifted boundary method, we solve a simple elliptic problem on this, right? Similarly, on the left is the Texas armadillo, and we do something similar there. Now, then when we were thinking about this, right? So we had a couple of questions, right? How does the quality of training of my implicit neural representation or a neural shifted of my neural level set, how does it impact how well I'm capturing my interface, right? And if I have a perturbed interface compared to my true interface or true geometry, if I have a perturbed geometry, how does it impact my solution? So the first question that we asked ourselves is, when is a learned implicit neural representation analysis suitable? Okay, so essentially, my student Samudra Karki figured out some actually very simple requirements. All we want is, so here is essentially a circle, and here is the true level set of this circle, right? So all that we want phi to behave is that it should behave like a sign distance field. It doesn't have to behave like a sign distance field everywhere. It just has to behave like a sign distance field in a narrow band around my true surface. So this significantly resolves or removes a lot of our computational issues with training neural level sets, right? So all it has to satisfy is these two conditions. It has to satisfy a non-degeneracy condition. That is, the gradient of phi should be bounded from below in a small neighborhood, and the curvature should be bounded from above in a tubular neighborhood. That's all, right? And so I can have the standard level set at the bottom. I can have a quadratic function that still has the same. So this is essentially r square minus 1, right? So this is a quadratic function, and this can be a truncated quadratic function or truncated level set. All these three functions, right, can serve as a valid sign distance field, right? So valid phi for performing analysis, right? So this was pretty amazing for us, right? So I don't have to solve the iconal equation to get a level set. As long as the level set behaves, as long as my implicit neural representation behaves like a level set close to my in a narrow band. Second is, well, if you look at the figure on the bottom here, what Samudra essentially did is he increased the amount of training of my INR. So you see that in the bottom left, it's pretty jagged implicit neural representation. And as you increase the amount of resolution or increase the amount of training, it becomes smoother and smoother and smoother and becomes closer and closer to the iconal equation, right? So then we asked ourselves the question, well, if I have a neural level set, the zero of the neural level set essentially defines a geometry. And I have, so it might be slightly off from the true geometry, and that's slightly off the distance between the zero level set of my implicit neural representation and my level set, my true boundary. I can bound it by, I can evaluate the difference with the Hausdorff distance. Now, can I bound this Hausdorff distance by the training error of my implicit neural representation? Because if I know how much loss my loss is going down, if that gives me a handle on how good my zero level set is, right, that's going to be useful for us, right? And so again, this is Samudra was able to get some very nice regularity conditions, right? So essentially, if gamma is my true level set and gamma p is a level set, the zero level set represented by the INR, right? We were able to show that the distance between gamma and gamma tilde, or gamma and gamma p, right, is bounded by my loss, my training loss, right? Training loss essentially is if I have my true level set, if I have my learned level set, I sample at a dense sampling of points in my domain. The error between them, the level set over the level set field, is bounded by epsilon naught. And essentially, what we show is the Hausdorff distance, the distance between the true level set, the true surface, and the INR surface is bounded by this epsilon naught. And so these are the figures on the left, and these are essentially the trained INRs, and we see that empirically they follow this lemma. Now, I want to pause here for just a second, and in the next 4 or 5 minutes, I want to make this point, right? So we start with, say, I'm given an INR, and I'm training this INR to some accuracy, right? With this rule, with this lemma, I'm able to connect that with how good am I representing my shape, okay? Now, if I know what DH is here, if I represent this shape error, then what we were able to show is we're able to show how well does the shape error propagate into my solution if I'm using a finite element based approach, right? So that's the theorem here. We show that the error, right? So the L2 error for an linear elliptic equation is bounded by two things. The one thing that we know and love is the right hand side, the second term there, which is the slope of given a mesh size of h mesh, and given essentially an order of basis functions k, my slope drops is h power k plus 1. But additionally, you have a term that scales as linearly as my how good I'm capturing my geometry, right? And so here is an example, right? So Samudra then trained different implicit neural representations with increasing amount of accuracy, and then he solved a simple Poisson equation, and we are able to show that this is essentially when h is very small here, right? So all the error is bounded by this dh, and you get a linear slope as expected, right? So this is essentially the L2 error for a Poisson equation follows a linear slope, right, in terms of the quality of your surface reconstruction. Now, when you let both of them vary, what you see is initially your error drops quadratically for a linear basis function, where it's determined by the second term in this expression, and at some point it asymptotes out when most of the error is driven by your interface representation error, right? So this is essentially tells us again a very simple rule of thumb. If you have the smallest mesh size that you want to use for a problem, that gives us a handle on how well to train your INR, right? How well to represent your implicit neural representation or a neural level set, so that is not the bottleneck in terms of your resolution, right? So essentially, we show that if you train your losses epsilon naught all the way down to h power k plus 1, then you're good, right? That's not going to be the bottleneck in terms of your resolution. So with all this, essentially coming back full circle, in the next 4 minutes, I'm going to give you some examples. So what did we do? We started with a neural implicit representation. we use the neural implicit representation with the shifted boundary method essentially. So we don't have to create the geometry. We replace mesh the geometry with something simple as evaluate the neural level set phi and gradient of phi, and then run the solver. And we show it essentially for an increasing sequence of complex PDEs. Right. First, we start with the Poisson equation that I already showed you. Then we're going to look at linear elasticity, and then finally with complicated problems involving Navier-Stokes. Right. So simple linear elasticity, we regain the expected slope for linear basis functions. Then Samudra took this out for a ride. He solved it for increasingly complex INRs, right? So here is your bunny, right? And then he also took it out for a ride in terms of creating an implicit neural representation, a neural level set for the Eiffel Tower, and then running your simulations on this, right? Next, I'm going to talk about extending this to Navier-Stokes equations. Simplest thing is our canonical example is the level set for a circle, and we immerse this level set for a circle in a background mesh and solve the lid-driven cavity problem. Essentially, I have u equals 1 on the top, and then that causes fluid flow, and this immersed geometry essentially blocks the flow. And if you notice here, this is we created a body-fitted mesh using Gmesh. We solved the problem, and then we used the neural SBM approach, and we solved this problem. And you see the overlay, right? And then I increase the Reynolds number from 100 to 1,000 to 5,000, and it works. And then here is an example for a sphere. And then Samudra asked the question, well, how does it work for more complex objects, right? It works for a cone. It works for a cylinder. It works for a multi-shaped, I don't remember, octagon, dodecagon. And then it works for the bunny. It works for slender objects like here in this case, a turbine with slender blades. And then finally, this is an exciting example where creating the mesh for this would be a nightmare. This is essentially a gyroid surface, and this acts like a membrane. So I'm going to we put this into a pipe, and we applied a Reynolds number of 10 pressure flow around this. And so we use this. We represent this object using a neural implicit surface and perform the analysis, and we're able to get it is much more difficult. We spent a tremendous amount of time creating the body-fitted mesh for this, several days, in fact, whereas this was completely automated in a couple of minutes to perform this analysis, right? Then finally, here are some last action shots, if you will. We took the implicit neural representation of the Stanford bunny, and we put it into a channel flow, and we were able to get the channel flow here, right? So finally, my concluding slide here. The big picture takeaway from is that we were able to eliminate the geometry explicitization. That's the detour that is often used in multiphysics simulations when we are given an implicit representation. Right? Usually we convert the implicit representation to STL file, immerse the STL file, and solve it. Right now we show that this implicit neural representation with this octree SBM, right, is algorithmically aligned. It's a very promising approach and this becomes more and more promising with all the push towards AI, right? So where we are getting more and more techniques for very quickly constructing implicit surfaces, right? So view synthesis algorithms, neural radiance fields, Gaussian splats, and variants of those that essentially give you, in some sense, an implicit representation of your object. And this framework allows us to take that implicit representation and actually perform analysis, right? And the key takeaways here are, we look at it from a math lens. We ask ourselves, when is an implicit neural representation analysis suitable? We provide bounds on how much it has to be trained, and link that training with how good the zero level set is being constructed. And we then translate that error in reconstruction of that zero level set and propagate that to our PDE. And essentially, we have a simple rule of thumb that enables ideal compute effort, and that is, train your neural implicit representation to h power k plus 1 if h is your finest resolution that you're looking for, and k is the order of your basis functions that you're going to look at. Right. So we showed validation across Poisson equation, elasticity, incompressible flow. this opens up a lot of possibilities. Fluid structure interactions, other multiphysics flows, also allows a lot of fast design iterations, right? So because we are able to modify the INR, and this is another work that Samudra has recently done. Stay tuned; it's going to come out on archive imminently. And so essentially, we modify the INR without having to rerun any remeshing, right? So this is work. Again, I want to emphasize that this is collaborative work across multiple groups that I am eternally grateful for working with. But this is work done by students in my research group. Kumar started the SBM work. Kumar started the Octree work. Chengao did a lot of the shifted boundary method on Octree's work. Mehdi is implementing this on GPUs. And most of this work that I presented today was done by Samudra Karki, who's a graduate student in my group. So with that, I thank you for your for attending this talk, and happy to take any questions.
Thank you, Baskar, for the amazing talk. So the floor is open for questions.
Hey, Baski, this is Setu.
Hey, Setu.
I was actually, so the Taylor series expansion for the immerse boundary method. So I worked a lot with patient-specific models. I was curious, at what point does it break down? Like, are there any conditions on the smoothness of the surface?
Great question. I think I can answer this, but Guillermo Scology has already shown that, right? So essentially, that's the reason why you start. You do the Taylor series not from the true surface, which can have sharp corners, but from the surrogate surface, right? And then all you do is you take Gauss points on the surface and find out the closest point. And the key thing where it'll break down if the closest point is too far away, right? And the error, like I showed, scales as d, right? And so the further away you are, the worse it gets. And that's why adaptive meshing is super useful, and that's why adaptive octrees are super useful. You can adaptively refine arbitrarily to get close to the true surface.
Got it. So it's around the smooth surface that
Yes.
you. Okay, thanks.
I give the chair to Aditya, that will be chairing the next talk. Aditya, please.
Yeah, thanks, Gianmarco. Thank you, Baskar, again for a great talk. So our next speaker is Dr. Yang Liu. He's an assistant professor in the Department of Mathematics at the National University of Singapore. Dr. Liu has received many awards, including the NUS Presidential Young Fellowship. He's interested in building foundational AI models for scientific challenges, including multiphysics prediction, control design, inverse problems, etc. Today he's going to talk about towards large scientific learning models with in-context operator networks. Yang, floor is yours.
Hi. Hello. Okay. Thank you again for the introduction, and also thank you, Baskar, for the great talk. So I think we have basically like seen this kind of future paradigm shift in a lot of scenarios. So people are talking like previously the previous like industrial designs like people like human experts try to make the design based on their knowledge or experience, and then we try to evaluate the design with classical simulations and experiments. So this whole process is usually like slow and rely on human expertise, and sometimes you have limited capacity to optimize. And okay, our hope is that in the future we can use generative AI to design things, and then we can use AI accelerated simulation to evaluate such design. And in the end, we can still validate this design via classic simulation or experiments. So we hope that we can have a faster iteration, and this whole process is data-driven, so we do not rely on human expertise anymore, and we have continual refinement because this whole process is like you can keep improving the simulation and also the generative AI, right? But I would say this future has not really come, not really like come to us in at least not in not everywhere. So that's why I'm now trying to revisit the current frameworks of machine learning for scientific computing. Okay. So I think firstly we can like very popular paradigm is the physics-informed neural networks. So in this framework, we are using one model to approximate one PDE solution usually. So here I'm giving like a illustration. So here we are using neural network to solve I think the wave equation, and the input of the neural network is this spatial temporal coordinate, and the output represents the function value corresponding function value. And the training of the neural network is essentially induced from the PDE and also the initial boundary conditions. So this pattern definitely achieved a lot of success, but we still have to tune the model when the solution function changes, right? Because we're using the neural network to approximate the solution function. So then we also have the operator learning. So here's the operator or neural operator. So here basically we use one model to approximate one operator. For example, the DeepNet or FNOT, which are two popular model architectures. So so here also like an example. So we can basically for example, we can define the operator that maps the initial condition to sometime later. So so we can basically train the model with a bunch of initial condition and like the terminal condition pairs, and if we're lucky, then give me a new initial condition. We do not need to train the model again. We just feed it into the model, and the model will give a prediction. Well, this somehow definitely is better than like pings, because now after training we do not need to train the model again for every solution function. We just need to like feed the initial condition. For example, in this case, initial condition to the model, and the model will make a prediction. However, I mean, the question is, what if this dynamic changes? What if the physics change? We still have to tune the model again. Right? So we still need to like, because here we are using one model to approximate one operator. If the operator changes, the model still needs to change. Okay. So in conclusion, I would say the current frameworks we're using one model to approximate one solution or one operator. They basically lack the adaptivity and require frequent retraining or fine-tuning for individual systems or tasks. So I'm asking myself, what do we really need? So I would say I really need a single model for a wide range of scientific computing tasks. We need this model to be able to instantly adapt to unforeseen systems or tasks without retraining or fine-tuning. So this is the next stage I'm thinking. So we need some kind of intelligence that can adapt to new physical systems or tasks. Okay. So on the other hand, we actually already seen the advances in generative large language models. So previous language models, they still like train they use a task specific data set architecture a lot to train a task specific model, but the GPT is different in that you can actually use this one model for a broad range of tasks. This is what we call foundation model. And let's say I think everyone here actually use AI every day. So we do not need to like we just like specify the tasks to in the prompt, right? And then the model will just solve the problem fast. We do not need to, let's say, retrain the model for every task. So this is very good. So the idea underlying is called in-context learning. So firstly, we need to unify multiple tasks with a so-called next token prediction. So next token prediction is like this, right? So for example, I saw a cat, and I'm trying to ask the model to predict the A based on I saw. And we specify the task in the prompt, that is the model input. And this prompt can include instructions, background, examples, etc. And then there's no training for each task. So for example, I give like a very simple example how to like reformat the date. So suppose this is our input and this is our target output. So previously, if I want to finish this task, I will train the model to map the input to output. But now with in-context learning, we'll now feed the model with this in-context example and also this test example in the model, and then ask the model to make the completion, and the model will be able to learn the pattern from these in-context examples and apply to the new test example. So that's the difference between this like in-context learning and previous learning framework. So inspired by this kind of large language model, we propose the in-context operator learning, which is a new framework for scientific problems. So the idea is that we want to map the textual or numerical prompts to scientific computing solutions. So in one forward pass, we can learn the solution operator from the prompt and solve the scientific computing problems without weight updates. And we can solve a wide range of scientific computing problems with a single model. So we efficient. So this is good because we have efficiency in marginal cost, and we can become more powerful for individual tasks due to cross the task knowledge transfer. And okay, hopefully we can have emerging capability when scaling up. It generalizes new tasks beyond training distribution and potentially even beyond human expectations. Right? So okay, this is the demonstration. So like we can have like a text prompt and this numerical prompts. So numerical prompt basically like consists of examples of operator input and output, and then the new input. And I will expect the model to learn the operator from this example and optionally this caption, and then apply to this new question and make a prediction. Okay. So okay, now I want to like give like a more detailed like problem setup. So firstly, we unify scientific computing problem as operator approximation. So here the operator basically a map from one function, I call it condition, to another function, I call it quantity of interest, or QI in short. So many scientific computing problems can be formulated as numerically approximate operators. For example, you have forward time independent PDE, you can have a coefficient field to solution, and the inverse time independent problem, you have solution to coefficient field. And you also have a forward time dependent PDE, you have initial condition to terminal solution. And also like even for optimal control, you can have mapping from the current state to control signal. So these all can be viewed as some kind of operator. And in particular, let's say this conservation law, right? So you can have let's say this is the equation. Sorry, this is the equation, and we can define the operator that maps the initial condition to some time later. And this operator definitely depends on the flux f here and the tau, and maybe the time, the time gap tau here. And if you suppose we need to approximate a new operator, right? And in classical operator learning, let's say we got some samples, sample pairs, right? So we use this sample pair to train the model, and then do the inference. During inference, without weight update, we are able to like predict the new output from the new input, right? But in context of learning, in our setup, it's like we basically feed all these examples and this new question into the model, and without weight update, during just with one forward pass, the model will be able to make the prediction. So that's it. Okay. So I think I will pause here to ask whether you have any questions. Okay. So I gave a very brief introduction of the architecture here, but this is kind of like a technical. So this is the architecture is standard decoder only transformer, just the same as large language models, but with special attention masks. So this is attention mask. So it looks very like a little bit complicated, but the idea is that we have so-called next function prediction. So the input is textual caption tokens and example sequences, and each function is represented by a sequence of vectors. So every function is not one token, but a lot of tokens. Okay. And the training, the training scheme is next function prediction. We want to predict the QI based on the captions and previous examples and the current condition. And for the inference, we can have flexible number of examples, flexible data points in each function, and then evaluate the solution function anywhere, basically via called query. And this process is in parallel and independent. Okay. So in our first paper, we basically solved these 19 families of problems with a single model. So for training, we have 1,000 operators for each problem family, each with 100 examples. And for testing, we have other operators, but only have at the most 5 examples in the prompt. So you can see in this problem, you have like a forward and inverse ODEs, PDEs. And most of them are one-dimensional, but you can also have one two-dimensional problem. There's no problem with it. So basically, one model can also handle different dimension problems. Okay. So maybe I think we can have some time to like have a quick look. For example, this is the let's say this forward problem of this ODE. Okay, very simple ODE. And I would say maybe the condition is the this is the inverse problem. The condition is a U, and I want to infer the C control here. But with different A1 and A2, this operator is different, right? So I really want the model to be able to infer, implicitly infer the A1, A2 as a parameter, and then to predict, from the examples, and then to predict the C corresponding to the input U. Okay, so as we can see here, for most problems with up to 5 examples in the prompt, the error can be reduced to like 1 or 2% for most cases. So I think this is like the general result. So here I'm illustrating some of the cases, right? So here. So for example, this is one case. So here the gray dots are the numerical prompts, and blue dots is a question, and red dots is a prediction. And this black solid line is the ground truth. Okay, so we can overlap with ground truth very well. And you can see this is another problem. So they are different. ODs or PDs, and here we have uniform grid, but here we have like flexible grid. So this stuff is very flexible. Okay, and also the number of points for each function is also flexible. So this is a 2-dimensional problem. By the way, this 1-dimensional, 2-dimensional problem are solved with a single model. So this is not a different model. This single model can solve different problems. So this is like a mean field control problems. So basically, like you try to solve this problem. And here the operator is the density field in the spatial temporal domain. Try to map from here to here, here to here, and here to here, and here to here the terminal cost G. Terminal cost G here is a hidden parameter. Is a hidden parameter. So we can learn the operator from the 3 examples. I would expect the model to learn the operator from these 3 examples and then make prediction corresponding to the new input. Okay, and basically here's the ground truth and this prediction, and the error is also like 1 or 2%. So I think so this is the example. Okay. So I also want to have some comparison with the classic experimental comparison with classic operator learning. So let's suppose this is the space of operators. Suppose this is space of operators. So in classic operator learning, we will train one model to approximate one operator, and then we fine tune it to approximate the neighboring ones. But this fine tuning is endless. It's endless. Also, when you fine tune the model to process this new one, it basically forgets this or the previous one. So this is always trying to approximate 1 point in this space of operator. But in context operator is that is trying to approximate ask the model to be able to handle a distribution of operators. So if the new problem is in the trend distribution, or basically like here you have generalization, they are very lucky. But if you still cannot solve it, you can still, in principle, you can still fine tune the model to add this place, right? So basically like we present the F1 to fit the forward operator of flux. So this is exactly the conservation law. Is about here. This is F, and then fine tune to approximate others. So with the FNO, so with pre-trained model, of course, it is able to handle this exactly this operator. But with the other operators, of course, you have some error. Then you can basically say, okay, I can fine tune this FNO to approximate other operators. Well, if this one, okay, this red one is very similar to the black one. So you only need 5 examples to be able to approximate the new one. But for others, like this green one, basically you need at least 300 examples to approximate the new one. And also, but with the in-context our so-called icon in-context operator networks, with 5 examples, we can basically approximate all these problems. Okay, and also like the inference of icon is super fast, just like 3.5 milliseconds. But with FNO, we have the inference is very fast, but the fine tune of of every step fine-tuning is time cost, time costly. It takes like let's say 7.4 milliseconds. Okay. And by the way, so I didn't put it here, but the whole fine-tuning usually takes like hundreds of steps. Okay. So we also basically developed this model to solve like let's say 2D Navier-Stokes equation with so-called vision inconvex operating networks. So it's basically similar, but instead of using point to tokenize the function, now we are like tokenize the fluid field with patches. Okay. So we can go through it like this. Okay. Maybe I can just show you the results. Okay, so so basically we have like a few initial frames to help us build a prompt. But this the process of building prompt is not the same as like from sequence to sequence, but instead it's like building examples. For example, so this is one pair, this is one pair, and this is one pair, and maybe for another data set, I can say this is a pair and this is a pair. So you can see that now we can build the operator with different times with different like I would say different equations and also different time strides to get different operators, right? So this is you can build the prompt, build the example in this way, in very flexible ways. Okay, so this is so 2D Navier is compressible. Okay, it's compressible. So in the end you have prediction. So the error is it's not that bad, I think. And also have an incompressive one. So this is done by the same model. I mean, the compressive one and the incompressive one is trained is solved by the single model. So that's the interesting part. Okay. By the way, this work is done. Basically, like a few time, like a long time ago, and at that time we don't have really like a lot of computational resources. So this is a lot of computational resources. So this is basically trained with maybe two 4090 GPUs for only 1 or 2 days. So it's not very expensive. The model is like it's like a 50 million parameters. So it's a very small model. I think we can basically try to have some conclusion now. So we basically draw the inspiration from large language model and propose the in-context learning framework and the in-context operator networks. The model can learn and apply operator in the forward propagation instead of approximating a specific operator. Therefore, can handle a wide range of scientific problems. So this icon shows the advantage compared with classical operator learning, the pre-training and fine-tuning, and show generalization to new PDEs, not just memory and training PD. So this can be extended to multimodal learning and has an intrinsic connection with Bayesian learning, and show the potential of foundation model for scientific computing. Okay, so here's the reference. So we have the first paper published 2 years ago, basically more than 2 years ago, and published on PNS, and also we have a few follow-up papers. Yeah, so you can check the code here. And this is my group website. So you can see more details and also the latest update. And some of the work is supported by the NUS PIP funding. And this is the QR code for my group. Okay. Thank you. Any questions?
Right. Thank you so much, Yang, for a great talk. So we're going to open the floor up now for a Q&A. So you can ask both the speakers questions. Please, you can unmute yourself to ask questions. If you want to raise your hand to ask a question, that's also okay. And you can also chat in the comments. You can also leave a question in the comments, in the chat.
Hi, Aditya. Can I go ahead and ask a question?
Yes, please. Please go ahead, Sushanta.
Hello, Yang. Great talk. I thoroughly enjoyed it. I'm Sushanta Ghosh from Michigan Tech. Do you have any comparison of the computational effort required to train these things and maybe standard numerical method like finite element or finite difference for solving one problem?
So okay, so I didn't really compare this song with the classic numerical solvers in a very I wasn't I didn't really compare that in a very fair way. So so here although I listed the window method here, but I would say the window simulation here, you can say that is kind of slower than icon, but window here serve as the ground truth. So it's like the golden standard baseline. Golden like it serves as ground truth. So it makes sense that is slower, right? So I don't think this is a fair comparison. I just put it here as a reference. Okay.
So is this the training cost or is this the cost of inference?
This window method is just simulation. There's no, I think there's no training, right? So this is the weighted, essentially non-oscillation. So this is like a very classic simulation method. There's no training
Numerical method. Okay, I see.
Yeah.
I see. Now, do you have any comparison for like a general problem like Navier-Stokes? How much computational cost is required to train? Because in one slide you mentioned that you have 19
okay. I got
operator.
I got the idea. Yeah. So
19
I think
operator.
okay. Yeah. So okay, this is a very good question. So essentially for every machine learning, basically you need to in a lot of problem in a lot of like papers people compare the inference with the classical numerical solvers, and this is not that fair because the training process is not taken into consideration. So right. So here I want to remark that the training of icon is also very like time costly. But the issue is that like this kind of like this model is able to solve a wide range of problems. So this is kind of like better than classical operator learning, because classical operator learning you have to like you have to like retrain the model for basically every new problem. But here we have the hope that for new problem you do not need to train again. So I never expected that the training of icon is even comparable to classic simulation. It's all about the marginal cost. But and also that if this model can solve a wide range of problems, so this training would be would worth it.
All right, thank you.
Yeah. Thank you for a great question.
Right. Yang, there's a question for you in the chat from Mohammed Hashimi. So I can read the question for you if you cannot see the chat. So Mohammed, if you're there, you can unmute yourself and ask the question.
Let me take a look at. Okay. Could you please comment on the accuracy of icon compared with DON or any hallucination with the so may I ask like what is the full name of DON? You mean deep operator network?
Yes, deep operator networks.
So in the I would say FNO can be viewed as like at least as simple as similar to the DON or as a type of DON. So let me try to share it. Okay. Wait for a minute. Yeah. So this basically like a given. So this is like the same size same number of parameters, same number of parameters. Okay. So with sufficient training data, this is kind of weird because like for the F1O, you want to train it to fit one operator, you actually need a lot of need a lot of data. But for like icon, you do not need a lot of data for every operator. So this comparison is kind of hard, right? So but with sufficient training data, you can this F1O can perform better than icon for a fixed operator. But it will definitely not work for others. And you need more data, a lot of time to retrain it or fine tune it to fit the new one. So that is the comparison.
Thank you so much. And could you also comment on the hallucination problems? Have you observed any such problems
Yeah,
in
hallucination. Yeah,
Yeah.
hallucination. Honestly, for now, I'm not sure whether it's a hallucination. But if your problem is significantly like audio the training distribution, you will have a wrong prediction. So from my point of view, like this kind of hallucination is in the scientific machine learning. What do you mean by hallucination? It just mean from my point of view, it just means like wrong prediction.
Yeah, I agree. So, for example, if the problem is much different than the training data set,
Yeah.
we might see some hallucination, I guess, right?
Yeah. Yes. Definitely.
Yeah. Thank you so much.
So,
Thank you.
yeah, thank you.
Are there any other questions for Bhaskar or Yang?
Yeah, I have a quick question for Yang. This is Baskar. Yang, great talk. So can you go back one slide and can you provide some insight into what is the complexity class, right? How much parameters you need in your model for the icon, right? Versus if I do FNO, right? Because in some sense, I like the previous slide number 15. Can you go to slide number 15? Yeah, this one, right? This is, I think, a very beautiful slide because it tells you in function space what they are. So essentially, you're saying pre-trained models are point models, whereas your icon is essentially pre-trained model that can essentially handle a whole space, right? So that means the complexity of your architecture should be sufficiently large to be able to capture this, right? So can you give us some? Do you have a feel for how big the complexity class should be for training these large pre-trained models?
I cannot give a very like a quantitative like a number on how many parameters you really need. This is somehow like a scaling law, right? So with some experiments, you can basically like say, you have some empirical observation on how many parameters you need, how many training data you need to get a loss down. But I somehow can basically say that for if you if you just like want to solve like one operator, at least I would say or maybe I should say in another way. So if you have FNO or icon with the same number of parameters, and FNO only focus on one operator, but icon focus on multiple operators, then FNO will perform better. This is something I can say. But
Or
like
what if I have 10x more parameters for icon? Will it be better or 100x?
Yeah, I think 10 times. I think in the end it will perform better. You will catch up. I think in the end it will catch up. I didn't. So I better observed something. I didn't put it here, but in other problems, I somehow observed something similar to the scaling law. That better you give me more data and better and larger model, I can perform better. And this is kind of like a linear way.
Thanks. I think if you have that some insight like that, I think that'll be super useful because right now you have like 17 PDEs, right? What if I have 300 different PDEs, right? So then what is my complexity class and how big should icon be to be able to capture?
Yeah.
That would be very nice to have that.
Yeah, that's a very good question. So in our recent work, I didn't it's not posted yet. So we actually try to solve it like a material problem. We observed some kind of like scaling law. Like so in the end you can predict for if you want to get the error to some degree, you need how many parameters and you need how many training time.
Awesome. Thanks.
Yeah.
Are there any other questions?
Thanks for the nice talk, Professor Liu. And I have one question. Well, I'm kind of curious, what's the difference between the few-shot learning and your in-context operator network? I think the conception is very similar because you also fine-tune your model and just give a few demonstrations of that example, and then just inference, and the model just gets very competitive performance. It's very similar to few-shot learning. So, is your research equals to that kind of method.
It's mainly because like this, so this is called like the terminology of few-shot learning is a little bit vague nowadays, because some people will say, okay, I provide some examples and then I provide some data, a few examples, and then fine tune a little bit. They also call it in few-shot learning. So that's why I didn't use this terminology. I use in-context learning to make it precise that I'm now trying to learn from the context, learn from the prompt without fine tuning. Yeah, because I saw some papers are using few-shot learning to refer to something that still need fine tuning. So that is something I don't like.
Oh, I see. Okay, thank you.
Yeah.
More questions?
Hi, Norma here. I have a question regarding, can you hear me?
Yes.
Yeah, no problem.
Yeah, so I have a question regarding conditional physics informed neural network. If you are aware, like the conditional physics informed neural network are also a generalizable model to solve a variety of scientific equations. So how would you define, like, how would it differ from like your model icon? How would it differ from conditional physics informed neural network? Because both are doing the same thing.
Yeah, very good question. So let's use this stuff as an example, for example, okay?
Or sorry to interrupt you, conditional pins or agentic pins. So these are also working with a variety of scientific equations. So I'd be like amazed, how is it like different from icon?
Yeah, so okay, so I definitely include, okay, it's not just pins, but also operator learning. You can make the condition, you can make condition on parameters, right?
Yeah.
But the issue is that firstly, somehow when you like condition on parameters, you already assume that, firstly, you already assume that this model works for a certain family of problems, parameterized in some way. Yeah. And secondly, you are assuming that you know the parameter.
Yeah.
But iPhone don't have this assumption. Firstly, you do not need to assume it is like how some format or parameterization format. Secondly, you do not assume that you know the parameter.
Okay.
Yeah. And
Okay,
also, let's
sorry.
say for example, I mean just think about this like conservation law stuff. Well, if you solve with like a conditional operator, operator networks, operator learning, conditional operator learning, you basically need to like feed f this flux and fall into the model, right? But now we do not feed. We just give example and ask the model to learn from the examples.
Okay.
Yeah.
Got it.
Yeah.
Thank you so much.
Yeah, very good question. Thank you so much.
Thank you.
Right. Any more questions for the first or the second speaker? Right. Baskar, I had a question for you, if you can hear me.
Yes.
Yeah, so I wanted to, first of all, very nice talk. I just wanted to ask you, there are some, famously challenging problems in solid mechanics involving very large material gradients. So I'll give you two examples. One example is of an elastomeric composites, right? So you have a soft material, you put hard particles in the soft material and in a very, very high volume fraction, right? So the spacing between the particles can be very, very small. I was just wondering how your method would perform in those kind of problems in which you have these very, very large gradients. Conventional mesh-based methods typically struggle with that. Another example of such a problem is this so-called checkerboard problem, which I don't know if you're familiar with. It's essentially on the black boards, you have different material and then white corresponds to a different material, right? And then you can have very large gradients at the corners. And that's also a famously very challenging problem with the conventional mesh-based methods. So I was just wondering how your method would perform for those kind of problems.
Thank you for that question, Aditya. Unfortunately, I might have to give you a deeply unsatisfying answer to that. And the short answer is I don't know. But maybe the longer answer, and maybe Guillermo is there, so he can chime in also, right? So I think I would like to differentiate between two things, right? The major part of what I talked about is if you have a geometry, the question of how do you represent the geometry is the key focus is we said we can represent the geometry with a level set, and then the shifted boundary method. You can solve this by whichever way you want, right? So if I have a geometry, I can solve it by fitting a body plate mesh or fitting using immerse methods and whatever your favorite immerse method is, right? But the argument here is that if you have a neural representation of your complex geometry, then shifted boundary method is very natural to that, right? And we have tried shifted boundary method for very complex geometries in the context of fluid mechanics, right? And in the context of elliptic equations, right? Some of the geometries that we show, right? And INR plus SBM in the presence of octree meshes works beautifully well because you can refine where you want because of the adaptive octrees, right? So, and you can query the level set and then refine, and then you can have a posterior estimates that will refine everywhere else, right? But I don't think we have tried it for high contrast materials, right? Yet.
So we did, so basically we're a little bit complementary, me and Baskar, in the sense that in my group, we created a version of the shifted boundary method called the shifted interface method. So if you have a high contrast material, typically we model it with sharp interfaces, and we were able to solve problem with T-junctions, with materials that they have a million in the change of parameters. They do produce very large gradients, and things seem to work. I mean, we were using some benchmarks for body fitted grids, and we were at least as good as them. You need to basically use the method for as an interface capturing method more than a boundary method for boundary value problems. So with Baskar, my interaction with Baskar, we work mostly on CFD type problem, right? And some thermal problems. But the method has been applied to contact mechanics, to fracture mechanics problems, and yeah.
Okay.
Sorry to interrupt, Baskar. I mean, you should be at the
No,
center
but I think
of the
you are the best person to answer the question that I had, so I'm glad you stepped in. Thank you for that.
Thank you, Baskar. Are there any other questions for Baskar or Yang? All right. If not, then let me conclude by thanking again both Baskar and Yang. Thank you so much for giving two amazing talks. Really enjoyed your talks, and we really appreciate you taking time to give us this great explanation of your work. So thank you everyone for attending these talks. And please, you can, I suppose Baskar and Yang would be very happy to, talk to you more later about the research that they presented. So you can reach out to them afterwards to talk about the talks. All right, thank you so much, Baskar and Yang. And let's conclude here.